The greatest physics mind ever? Probably. But what is it that makes Einstein's ideas so revolutionary? Let's take a deep breath and start by looking at a radically new concept, the special theory of relativity. Our understanding of the physical world was completely turned upside down by Einstein, and this all started at the beginning of the 20th century. The 1905 paper, which we now refer to as the one for special relativity, introduced the principle of relativity and also dealt with a lot of other concepts. The speed of light, what we mean by two events being simultaneous, how lengths and times are measured by different observers, and how electromagnetic phenomena are considered by Einstein. All this is too much for just one video, so we will take our time and deal with the most important ideas one at a time in a few videos. Let's begin by simply stating what the special theory of relativity is and what it isn't. Special relativity essentially deals with the speed of light and the consequences which follow once we assume that the speed of light is fixed. That is pretty much it. What special relativity does not include is anything to do with gravity. That would follow 10 years later in 1915 in Einstein's general theory of relativity. But the thing to remember is that the two theories of relativity, special and general theory, are inextricably linked to each other. General relativity is the complete theory, but if we take general relativity and put gravity as being equal to zero in there, then we get special relativity. So special relativity is a subset of general relativity in the case where there is no gravity. And this is the same approach as if we ask how Newton's laws relate to special relativity. If we put the speed of motion as being very, very small or zero in special relativity, then we get Newton's laws. So if we are considering speeds of motion which are very small as compared with the speed of light, then we can simply use Newton's laws. Newton's laws can therefore be seen as a subset of special relativity in the case where the speeds of motion are very small. This idea of a theory being a subset of a bigger picture is the realization of the concept that we don't have to say Newton was wrong. It is just that where we can apply Newton's laws is limited to cases where the speed of motion is much, much less than the speed of light. This is why Newton's laws work perfectly well in human scenarios on or near Earth, but when we deal with stars and the universe, we have to apply relativity theory. If we're moving fast but not concerned with gravity, then we can use special relativity, and if we have to include gravity as well, then we use general relativity. So let us begin to look in more detail at special relativity, where there is no gravity, remember. Then slowly we will work up our ideas to the case where there is gravity and see what that means for our understanding of space and time. Before going into what Einstein proposed, however, it is helpful to mention the works of two other great physicists, Michael Faraday and James Clerk Maxwell. Einstein really admired the work of Maxwell in particular, so this is relevant to where the ideas of special relativity came from. Michael Faraday was a great experimentalist, and his demonstrations and lectures at the Royal Institution in London are legendary. Faraday showed how electricity and magnetism function, and his ideas led to so many things that we now take for granted. Most electrical things in the modern world use principles which Faraday demonstrated. Things like electric motors, electrostatics, use of magnets, how power stations generate electricity, even why an aeroplane can fly through a lightning strike because the shell of the aircraft is acting as what is known as a Faraday cage. Faraday's work showed the principles of electricity and magnetism in action and how they were interlinked, but it was left to James Clerk Maxwell to formulate a complete theoretical explanation for the effects shown by Faraday. Maxwell was a Scottish physicist and mathematician, and he published his theory of electromagnetism in 1873. Maxwell merged the ideas of electricity and magnetism into a single theory and provided a mathematical description of the effects shown by Faraday. Maxwell's theory also proved that light was an electromagnetic wave. In his theory, Maxwell provided 4 expressions for the behavior of electromagnetic waves. These equations, known as Maxwell's equations, describe mathematically how electric and magnetic fields behave and propagate. Maxwell's equations are one of the most challenging things that physics students have to learn at university, and we will not be inflicting that on anyone here. So we mention Maxwell's theory of electromagnetism not to go through it in any detail, but really just to show that from Maxwell's equations we can derive an expression for the speed of an electromagnetic wave. This speed c is given by the expression c is 1 over the square root of mu naught times epsilon naught, where mu naught and epsilon naught are the permeability and the permittivity of free space. The permeability of free space determines how the vacuum of space can interact with a magnetic field, and the permittivity of free space determines how an electric field can propagate in space. So this expression from Maxwell's equations shows that the speed of an electromagnetic wave is only determined by 2 constants of nature, and hence the speed of an electromagnetic wave must itself also be constant. And because light is an electromagnetic wave, it therefore follows that the speed of light is constant and has the same value as all other electromagnetic waves. This is a fundamentally important result, and this feature of Maxwell's theory is what Einstein would pick up on when proposing the special theory of relativity. The 2 constants, mu naught and epsilon naught, can be measured experimentally, and when we put in their values into the expression for the speed of an electromagnetic wave, we get the answer for the speed of light in a vacuum. The current best number we have for the speed of light is 299,792,458 meters per second. So roughly 300,000 kilometers a second, or about 186,000 miles per second. This speed means that light can travel 7.5 times around the Earth in 1 second. Einstein held Maxwell's theory of electromagnetism in the highest regard, and this is reflected in the fact that Einstein's Special Relativity paper was called On the Electrodynamics of Moving Bodies. Einstein was pursuing the implications of Maxwell's ideas on electromagnetism to their logical conclusion when applied to moving bodies. This was one of Einstein's amazing strengths. He was not afraid to cast aside an accepted orthodox view of a problem if logic and reasoning were saying something else. And the other astonishing skill that Einstein had was his ability to do thought experiments. In reality, that was the only way that Einstein could think about ideas to do with the universe, because there is no other way than to think what it means to move at the speed of light, or what gravity and space-time mean near a star. So this is why, in so many cases, Einstein's ideas are often best described by how clocks behave, or what people in rockets might feel, or even how trains move, because that is how Einstein conceptualized his thinking. He could not do real experiments in the lab, so he did thought experiments in his mind instead. We will try to use some of those ideas from Einstein's thought experiments to illustrate the effects of relativity. In the 1905 paper, Einstein proposed 2 postulates. Now, a postulate is a statement which is said to be true without proof, so it is taken as a starting point for a theory. As an example, I could postulate that on a flat piece of paper, a straight line can always be drawn between 2 points. Now, I can state that without proof, and we can see if it is always true or not. If the postulate is true, then there will be no loss of logic, and all the arguments which are derived from the postulate will be valid. If a postulate is false, so the starting point for the theory is wrong, then what follows from the postulate will be able to be falsified. That is, it will not agree with some other known fact or observation, or it will obviously be able to be contradicted. Let's look into these two postulates in detail because they are fundamental to all that follows. The first postulate that Einstein proposed was that the same laws of electrodynamics and optics will be valid for all frames of reference for which the equations of mechanics hold good. This first postulate was called the principle of relativity by Einstein, and basically says that the laws of physics are the same for all observers anywhere as long as they are in an inertial frame of reference. This is often shortened to say for all inertial observers. But what is an inertial frame of reference or an inertial observer? This is a key concept in the understanding of motion in relativity theory. So we will go into this in a bit of detail because it is very important to understand frames of reference, especially inertial frames of reference. A frame of reference is a description of the state and surroundings of a body, so it is really defining where a body is, how it is moving, and what other things are going on which affect the body. For example, is there a force or acceleration acting on it? In essence, the frame of reference of someone gives us their perspective as to what they are doing and how they observe and experience things. The term inertial frame of reference comes from Newton's first law, which is known as the law of inertia. As we have already seen many times, Newton's first law states that a body will remain at rest or moving at constant velocity in a straight line unless acted upon by an external force. So an inertial frame of reference or an inertial observer refers to a case where Newton's first law applies, which means that a body is at rest or in constant motion. This also means that there is no acceleration. We know this because if velocity is constant, then the rate of change of velocity, which is acceleration, must be zero. So in relativity theory, whenever an object is in an inertial frame of reference or someone is called an inertial observer, that means that the object or the observer are not accelerating. They are at rest or moving at constant velocity. Let's take an example to see what the postulate means. Imagine there are two people, Alice and Ben. Alice is inside a train carriage, but with all the blinds pulled down so she can't see out. The train is moving at constant velocity, and we assume that the train is absolutely silent and there are no vibrations. So Alice cannot tell if the train is moving with respect to the outside world or not. And Ben is at rest outside of the train on a station platform, but he's inside a closed box with no windows. In this way, we can say that Alice and Ben are in inertial frames of reference since they are at rest or moving at constant velocity. And neither Alice nor Ben can see or sense what might be happening outside of the train or the box. Now, what Einstein's first postulate says is that the laws of physics must be the same for both Alice and Ben. So if Alice and Ben both do the same experiment, then because the laws of physics are the same for both of them, they will get the same answer. Let's say Alice and Ben both drop an apple to the floor and work out its speed on impact and the time that the apple takes to drop, something we worked out in an earlier video. If Alice and Ben both do this experiment, then both will get precisely the same results. So even though Ben is stationary and Alice is moving at constant velocity past Ben, both Alice and Ben get the same results for the experiment. And because there is no difference in the results of any experiment that they can do, there is no way for them to tell if either of them is at rest or moving. The laws of nature are the same for both of them, no matter if they are at rest or moving at constant velocity, because they are in inertial frames of reference. This is the core principle of the first postulate. The laws of nature are the same for all inertial observers. And there is one more thing which is really important. the principle of relativity also says if both Alice and Ben had windows and could see each other while Alice moved past Ben, Alice could claim that she was at rest and that Ben was moving. This is the principle that in inertial frames of reference, there is no concept of being at rest. Ben and Alice can both rightfully claim to be at rest and say that the other person is moving past them. In simple terms, all Alice and Ben can say is that there is relative motion between them, but they cannot work out who is moving.
Let's look at this idea a bit further.
Let's say Alice and Ben are in two cars travelling in opposite directions, and both cars have a speed of 60 miles an hour. The 60 miles an hour is their speed with respect to the road, but of course they are also moving relative to each other. Now, it is obvious that the closing speed of the two cars as they pass each other will be 120 miles per hour. Alice and Ben will each measure the difference in velocity between them of 120 miles per hour. Similarly, if Alice is moving at 60 miles per hour and Ben is racing her and moving at 100 miles per hour in the same direction, then when Ben overtakes Alice, it will appear as though Ben is moving past Alice at an effective speed of 40 miles per hour. This is the difference in velocity between Ben and Alice. The point is that in everyday scenarios, physical objects which are moving have their speeds referenced against something else, and the relative speed which we measure is dependent on how one observer or the other is moving. What special relativity adds to this is that even if Alice or Ben are both moving, either of them can also claim to be at rest and just say that the other person is doing all the motion. So if Ben and Alice are travelling in opposite directions at 60 miles an hour, then Alice can claim to be at rest and say that Ben is doing all the moving. In this case, Ben or Alice will still measure their relative velocity to be 120 miles per hour, the same as before, but now Alice is claiming to be at rest. And of course, Ben could equally claim to be at rest and say that Alice is doing all the moving, and the relative speed would still be 120 miles per hour. And the same argument applies to when both are travelling in the same direction. Either Alice or Ben can claim to be at rest and say the other person is moving, and they will still both measure the same relative speed of 40 miles per hour. The key thing from relativity theory is that both Alice and Ben can claim to be at rest, and both will be correct in their own frames of reference. So from Alice's viewpoint, it is Ben who is moving, and from Ben's viewpoint, it is Alice who's moving. And neither of them could do any experiment to disprove their respective claim of being at rest. They are both correct in their own frames of reference. This may seem illogical or counterintuitive, but this is the main tenet of special relativity. We have to accept that what we experience in our own frame of reference, our perspective, is perfectly valid and cannot be disputed, but it does not mean that another observer in another frame of reference, their own perspective, has to agree. All inertial observers are perfectly entitled to claim their own frames of reference are valid and claim that they are at rest. This idea of relativity was not in itself new. Many others, including Galileo, had proposed a similar idea of relative motion. But it was Einstein who thought through the implications of relativity and proposed the radical ideas of what moving in inertial frames of reference implied, especially the idea of there not being a notion of absolute rest. The concept of relative motion is quite a subtle idea to grasp, but you may yourself have seen this effect in action. If you're sitting in a train at a station and there's another train right next to you, sometimes you can sense the train next to you as moving, but for a few seconds it is not obvious whether you are moving or the train alongside you is moving. That is because you cannot feel any acceleration, and all your senses have to go on is the relative visual movement of the two trains. After a short time, the illusion is broken, maybe because you see the other train has moved a bit and you can now see the station background behind it. So it is obvious that you have not moved. In such human scenarios like trains and stations, it is usually the context of the situation, like the background to objects or vibrations and noise, which give us the extra information about who is moving. But in the absence of such things, like in space, it is impossible to work out who is moving. More fundamentally, however, Einstein said that there is no absolutely correct answer as to who is moving. Two inertial observers, like Alice and Ben in space, can each rightfully claim that they are at rest and the other is moving. And there is no way to disprove that claim. Both are correct. This is really the core principle of relativity. The second postulate that Einstein proposed was that light is always propagated in empty space with a definite velocity c, which is independent of the state of motion of the emitting body. This means that the speed of light is constant in a vacuum, irrespective of how the observer or the emitter of the light is moving. That is, the speed of light is the same for all observers. This is also counterintuitive to our everyday experiences, and this was the other really revolutionary concept which Einstein introduced, saying that the speed of light did not depend on its motion or that of the observer. There were two things which led Einstein to make the conceptual leap that the speed of light was always the same, and that the speed of light was not measured with reference to anything else. The first part of this postulate, that the speed of light is constant, comes from Maxwell's theory of electromagnetism, as we've already seen. But what Einstein did was to add the second crucial part about the speed being irrespective of how the observer or the emitter of the light is moving. This was the truly revolutionary concept of this second postulate. This idea was radical because at the start of the 20th century, it had been assumed that light was a wave, and just like all other waves, the speed of light should be taken against some reference. What does this mean? Well, for example, a sound wave moves at a speed with reference to the atmosphere, and a wave at sea moves at a speed with reference to the ocean. In our everyday experience, we say a car is travelling at 60 miles an hour, say, but what this actually means is that the car is moving at 60 miles per hour with respect to the road. Or if a train is moving at 100 miles an hour, that speed is with respect to the train tracks. So all speeds in normal life are measured against some fixed reference. We just don't explicitly say that. This is the case with moving bodies, but Einstein postulated that light was the only exception to this idea of relative motion. The speed of light is always measured to be constant and never changes from its fixed value, no matter how the emitter or the observer of the light is moving. So imagine Alice is in a car moving at 100 miles per hour towards Ben, and Ben is standing at rest by the side of the road with a torch. Ben turns the torch on so a beam of light travels towards Alice at the speed of light c. When Alice measures the speed of light from the torch, we might expect her to measure the speed of light as being c plus 100 miles an hour, the speed of her car, like we would if there were two cars travelling towards each other. But what Einstein said was that Alice will still measure the speed of light as being c, not c plus 100 miles an hour. Even if Alice is moving away from Ben at half the speed of light, she would still measure the light beam from the torch as arriving to her at the speed of light c, not at half the speed of light as you might expect from what happens with relative speeds of cars. This part of the second postulate, that the speed of light is constant no matter how the observer or the emitter of the light is moving, was related to some other ideas which had been going around for centuries. We need to look at those briefly so that we know why Einstein postulated what he did. We've already mentioned that waves propagate within some medium, like sound waves in air and ocean waves in water. This was known going as far back as the Greeks, but when light began to be studied more seriously in the 17th century, There was no clear idea or consensus as to what the medium was that light travelled through, and that we could measure its speed against. One of the problems was that this medium would have to be everywhere because light was everywhere, and nobody could work out what this could be. One of the key people in these studies of light was Christian Huygens, a Dutch physicist, astronomer and mathematician. Huygens' achievements are extremely wide-ranging and truly groundbreaking. He developed analytical geometry, proposed ideas about gravitation and mechanics, discovered Saturn's moon Titan, invented the pendulum clock, and most importantly for us, he developed numerous ideas about light, which were published in his treatise on light in 1690. In this work, Huygens proposed the wave theory of light and laid the foundations for what we still use today, geometrical optics and how light propagates. Huygens' wave theory of light contained the notion of an ether, a medium through which light travels. Sometimes this ether was called the luminiferous ether or light-carrying ether. But this idea of an ether was at odds with Newton's thinking at the same time, because Newton had proposed a corpuscular theory of light. Newton said that light was made up of small particles, which he called corpuscles, which travel in straight lines at constant speed, but which do not require an ether. Newton did not like the idea of an ether because he thought that an ether would act to cause a drag on planetary bodies in orbit, something that was at odds with his theory of gravitation. So Huygens and Newton took opposing views on what constituted light and how it propagated. Newton thought of light as particles and Huygens thought of light as waves. It turns out that both would be proved right because we now accept that light can behave both as a particle and a wave, though the reasons behind Huygens and Newton's ideas were not fully correct at the time. Then later on, in the early 1800s, the British scientist Thomas Young theoretically confirmed Huygens' wave theory of light and also illustrated it by a series of landmark demonstrations. Young had used travelling waves in water in a ripple tank to show how the existence of waves can be inferred from interference effects, and he then extended this concept to deal with light. Young devised an ingenious experiment where light was passed through slits and formed interference patterns on a screen. This proved the wave nature of light. The modern version of Young's interference experiment, called the double slit experiment, is proof of the wave nature of light, but it now also serves as a foundational mechanism with which to discuss quantum theory. The idea that light can behave both as a wave and a particle would be formally proposed in the 1920s and is known as wave-particle duality, but nobody had any idea about this in the 1800s. So in the early 19th century, the wave theory of light was proved to be correct by Young, but the idea of an ether remained open. So what did light propagate through? Nobody could work out what the ether might be. Then in 1887, the American physicists Albert Michelson and Edward Morley devised an experiment to measure the motion of the Earth with respect to the ether. They thought of the ether like a wind blowing through space in a particular direction. And what they did was to set up an interferometer, similar to what Young had done, to measure the interference of light beams. Their interferometer had to be extremely stable because it needed to be very sensitive to make the measurements they needed. So they mounted the whole setup on a large stone slab and then floated the whole thing in a bath of liquid mercury to avoid any vibrations. The basic idea was that they would measure the speed of light with their interferometer at different positions of Earth in its orbit. Assuming that the Earth was moving through the ether in its orbit, at different locations, the Earth and the ether would be moving differently relative to each other. And this relative movement would cause a varying drag on the Earth and thereby cause an effect on the measured speed of light. This was not an easy experiment to perform, but Michelson and Morley did an exceptional job over many months, but the outcome was negative. No difference in the speed of light was found in any direction or in any position of the Earth's orbit. So the experiment did not prove the existence of an ether. This is probably the most famous negative result in physics. Nonetheless, for this experiment, Albert Michelson won the Nobel Prize for Physics in 1907, the first American to do so. But strangely, Edward Morley was overlooked. So at the start of the 20th century, we had a situation where light was known to be a wave, but there was no evidence for an ether. So nobody could say how light propagated in a vacuum without there being a medium to travel through. And Maxwell had said in his theory of electromagnetism that the speed of light was constant, and it had been measured. So the open question was, what was the speed of light being measured against if there was no ether? This seemed a real problem. This is where Einstein came in, and his revolutionary thought was that we don't need to have a medium for light to travel through. So light, or any electromagnetic wave, can travel through empty space without needing an ether, and there can be a constant speed of light without needing a reference medium. Light just travels at a certain constant speed all of the time, and it does so for everyone, no matter how anyone is moving with respect to the light. This was the basis for his second postulate in the Special Relativity paper. So there we have it. The postulates of special relativity give us the main features of the theory. So there is no concept of absolute rest in the universe, all motion is relative, and the laws of nature are the same for all observers in inertial frames of reference. All inertial observers can perfectly well claim to be at rest while saying that other inertial observers are moving relative to them. And finally, special relativity also states that the speed of light is constant and is the same for all observers, irrespective of their relative motions. The implications of these ideas are really far-reaching, and we will look at some of these in the videos which follow. The concepts of relativity can be mind-blowing and quite difficult to grasp. This is mainly because our everyday experiences don't align with what relativity says. But nonetheless, relativity is one of the most tested theories we have, and it has proven correct every time. I hope you have learned something new about the origins and concepts of special relativity, and until next time when we delve a bit deeper, keep thinking physics.